For years, generating high-quality, realistic images computationally was a holy grail. Today, we're diving into an idea that's delivering these results, as this paper describes, high-quality image synthesis results.
The images these models create are stunning, but when I first heard diffusion models, I immediately thought of, well, things spreading out and getting messy. How can that create order?
That's exactly the paradox we'll unpack. These are diffusion probabilistic models, a class of latent variable models. The diffusion part refers to a controlled process of adding noise.
So it's not diffusion in the sense of spreading out randomly, but spreading out in a very specific, controlled way?
Precisely. The inspiration comes from physics, specifically considerations from non-equilibrium thermodynamics. Think of it like watching a drop of ink diffuse in water, but then being able to reverse that movie perfectly.
Wow! Thermodynamics? That's not what I'd expect for image generation. Does that analogy of reversing the ink drop hold up well?
It's a useful starting point. The core idea is that if you know exactly how the ink diffuses, you could, in principle, reverse it. The challenge is learning that reversal implicitly.
So instead of explicitly modeling how images are formed, we're modeling how they're destroyed and then how to undo that destruction?
Essentially, yes, and the results are impressive. For example, on the SciFar 10 dataset, they achieved a state-of-the-art FID score of 3.17, which is a strong metric for image quality and diversity.
FID scores were a big deal when GANs were new. Does this mean diffusion models are replacing GANs, or are they solving different problems?
They operate on a different principle than GANs. GANs train a generator and a discriminator in opposition. Diffusion models have a fixed, noisy forward process and then learn a single reverse process.
So no adversarial training, which could mean more stable training. That addresses a common pain point we've talked about in previous episodes.
Exactly. They report on 256 by 256 LUSN, and they obtain sample quality similar to progressive GAN. This indicates high fidelity even for complex, larger images.
That's quite an achievement. So the question isn't just, can they generate images, but how do they manage to reverse this entropy-increasing process?
Precisely. The next step is to understand the two core processes, how noise is added, and then how it's learned to be removed. That's the heart of the intuition.
All right, let's trace this forward and backward path, starting with how data gets noisy.
Think of it like this. You start with a clear photograph. The forward diffusion process will slowly add random noise to data to that image over many steps.
Like repeatedly saving a JPEG at lower and lower quality, or adding static to a video, frame by frame?
Yes, but very specifically, it's a Markov chain of diffusion steps. This means each step only depends on the previous one, and Gaussian noise is added according to a schedule.
So you take x0, add a bit of noise to get x1, then add a bit more noise to x1 to get x2, and so on?
Exactly. After many steps, the data sample x to the power of 0 gradually loses its distinguishable features. It becomes pure Gaussian noise. The original image information is totally obscured.
So by the end, XT is just static. We've effectively destroyed the image. Why would we want to do that? That's my big question. If we just turn an image into noise, how do we get it back? What's the reverse part of this learn to reverse the diffusion process?
The key is that the forward process is fixed and known. So we train a neural network to learn the small incremental steps required to undo the noise at each stage. The goal of the reverse process is to recreate the true sample from a Gaussian noise input. You start with pure noise, and step by step, the model learns to remove the noise. So it's like having a crumpled piece of paper, knowing exactly how it was crumpled, and then learning to perfectly uncrumple it back to a flat sheet. That's a good analogy. The model doesn't just pull the image out of the noise magically, it learns to predict what noise was added at each step and remove it.
So at each step, it's trying to predict the noise so it can subtract it and get a slightly cleaner version of the image?
Exactly. This approach offers benefits unlike VAE or flow models. The learning process is fixed, not adversarial like GANs, which helps with training stability.
That stability must be huge. So it's a series of small, learned denoising steps rather than one big generative leap.
Right. The uncrumpling is not perfect immediately. It's a gradual, iterative refinement. The analogy breaks when you consider that we don't know the crumpling perfectly, we just learn to reverse its effect.
So the model learns the transformation needed to go from noisy to less noisy, not the specific noise value itself, necessarily.
Yes, and this brings us to the core mechanism. How do we mathematically define and train a model to perform this precise denoising? It's about predicting epsilon.
Okay, so from intuitive uncrumbling to the actual math of how it works. I'm ready for the technical details.
The forward process, adding noise, is easy to define. The challenge is reversing it, finding Q of xt minus 1, comma xt, meaning the probability of the slightly cleaner image given the current noisy one.
Why can't we just compute that directly? If we know how we added the noise, shouldn't we know how to undo it?
That's a common misconception. We cannot easily estimate Q of xt minus 1 given xt directly because it requires knowing the entire data distribution. That's intractable for complex real-world data.
So we have to learn an approximation of this reverse step instead of calculating it. That's where the neural network comes in, right?
Precisely. We learn a model p theta to approximate these conditional probabilities. This neural network, often a UNet, predicts the noise that was added in the forward step.
So the model isn't directly predicting the clean image x0 or even xt minus 1. It's predicting the noise component, epsilon, that allows us to go back one step?
That's a critical insight. The paper shows we can reparameterize the Gaussian noise term instead to make it predict epsilon of t. This simplifies the learning objective significantly.
So the neural network takes the noisy image x of t and the time step t as input and outputs the predicted noise epsilon of t.
Yes, and empirically, the original DDPM paper found that training works better with a simplified objective that ignores the weighting term. The loss function is surprisingly simple.
It's just minimizing the squared error between the actual noise and the predicted noise? That feels almost too straightforward for something so powerful.
It is, but that simplicity hides a deep connection. This denoising process has a strong connection with stochastic gradient Langevin dynamics. It's like iteratively refining the input.
Langevin dynamics? That sounds like another physics concept, like the thermodynamics from earlier. What does it mean here?
Langevin dynamics produces samples from a probability density p of x using gradients of that density. Imagine climbing uphill on a probability landscape to find dense regions.
So predicting the noise is, in a way, guiding us along the gradient of what makes a real image, gradually moving away from random noise towards actual data?
That's exactly right. This also connects to score-based generative modeling method, where the score is the gradient of the log probability density. Predicting noise is equivalent to predicting this score.
Okay, so the simple act of predicting noise at each step is actually guiding the generation process to follow the underlying data distribution's gradients. That's a huge shift.
It is. This mechanism is incredibly powerful. However, running this iterative denoising process on high-resolution images comes with a significant computational cost, which brings us to our next big idea.
So, great results, deep theoretical backing, but there's a practical bottleneck. What's the solution for making these models usable for huge images?
The issue is that standard diffusion models operate directly in pixel space. For a 1024 by 1024 image, that's over 1 million dimensions. Every denoising step processes that entire high-dimensional data.
1 million dimensions times hundreds or thousands of steps? That's an astronomical number of computations. It explains why they were so expensive.
Precisely. The paper states that optimization of powerful DMs often consumes hundreds of GPU days. That makes them inaccessible for many researchers and applications.
So the core mechanism works, but its application to high-res images is cripplingly slow. How do you maintain quality without that heavy pixel-level processing?
The solution is latent diffusion models, or LDMs. They apply them in the latent space of powerful pre-trained autoencoders. This is a crucial shift.
Wait, an autoencoder? Like the ones we've seen that compress data into a smaller representation and then reconstruct it?
Exactly. Think of it like this. Instead of adding and removing noise directly to the raw pixels, you first compress the image into a much smaller, information-rich latent code.
So the diffusion process happens on this compressed representation, not the full image. That's clever, but won't you lose detail?
The paper claims this approach allows them to reach a near optimal point between complexity reduction and detailed preservation. The autoencoder captures perceptual details effectively.
So the autoencoder acts as a perceptual compression layer. The diffusion model works on the essence of the image, not every pixel.
That's a great way to put it. This latent space also enables a powerful addition by introducing cross-attention layers into the model architecture.
Cross-attention. That's what we explored in case TCM-033005. Does that mean LDMs can take text prompts, like transformers do for language?
Yes, absolutely. Those cross-attention layers make them powerful and flexible generators for general conditioning inputs, such as text or bounding boxes. This is key for applications like stable diffusion.
So by combining the denoising idea with a smart compression step and attention, they get high quality and controllable generation. That's a huge leap.
It is. The latent space operations are much faster, significantly reducing computational requirements compared to pixel-based DIMs, making high-resolution images practical.
This means we can run these complex models on consumer hardware, leading to a huge explosion in applications. It's like the transformer moment for image generation.
Precisely. Latent diffusion models offer a robust framework that balances quality, computational efficiency, and creative control. When you need high-fidelity generation that's also steerable, this is the idea you reach for.
I'm Maya. Thank you for thinking this through with us.
I'm Arjun. Another idea in 3 hours. Take care of your mind.